Good morning, good afternoon, and good evening, and welcome back to the Friday Talk Show with your host Rajiv Kulkarni. Today's date is 21st of August 2026, and today we are here with yet another topic of everybody's interest and a continuous sequel of previous topics, I would say. But To bring that, we have the technocrat, technology expert, I would say, from the Silicon Valley of India. And today I am talking from the Silicon Valley here in the United States in San Jose. So it's early morning, 7 o'clock here in San Jose, and every Friday we bring this show 30 to 40 minutes to talk about electronics manufacturing and the various market segments in the electronics, how it is impacted or it is impacting the electronics market segment in the manufacturing side of it. When we say electronics manufacturing means we are talking about the design from the design level to the mass production level and various aspects that goes into the electronics manufacturing activity, whether it's a design of printed circuit boards, whether it's supply chain, whether it's process engineering, the validation, the test methodology, NPI, and so forth, and finally the production and execution of certain product, right? So in today's world, because of the AI and data center market is exploding at a very exponential rate, and the growth rate is very high, and also the AI market is engaged in all different fields, right? Last week I started at another sequel of subject, which is data center and impact on electronics market, right? So as we spoke that the application is huge, the application is wide, so does the electronics is growing from that perspective. So ladies and gentlemen, today's topic is depletion wave in PDN for HSIO boards, and it is the sequel of physics-based HSIO interface routing, and the episode number 9. The synopsis goes like this: the depletion wave or spatial voltage depletion front refers to the radial transient voltage sag wavefront that expands across the power ground plane cavity when a SerDes driver rapidly draws dynamic current. So let's welcome Mr. Ambaprasad, the technology expert who has more than 4 decades in the industry, and he lives in Silicon Valley in Bangalore city in southern part of India. And so welcome to the show, Mr. Ambaprasad. How are you this evening?
Doing good.
Excellent, excellent. So let's start our today's topic, and I will present the screen, and I will share the screen and present the presentation that you have shared with us. Give me 1 minute here. And here we go, and make it big so everybody can
Page
see.
number 103. Go full size.
It's
Good.
already full size. Yeah. Okay, let's start.
Let's start. This is where we stopped our previous event, previous session. We told the power PDN, the power distribution network verification, its power integrity, it all depends on what we called as depletion wave. So before we start, let me tell you what is depletion wave. This was told to me in one of the classroom sessions by Madhavan Swaminathan of Guitar Tech. So what he told is, let's say you're doing some exercise in a gym, you get thirsty, you want to drink water. You drink water from a glass, and then you consume a glass of water, and that glass of water is depleted. It's gone. Now that has to be replaced. And again, when people drink water from a dispenser, they exhaust a dispenser also. Now, let's say 10 people are drinking water, even dispenser gets emptied. Now, dispenser has to be filled up. That is filled up by, let's say, the floor water tank. And then by the floor water tank gets filled by the building water tank. Now, the building water tank has to be filled up by the community water tank, the corporation water tank or whatever we call. So as you start consuming power at a very small quantity, that has to be replenished. So the depletion wave is the one which sends the power demand across the PCB from the chips to PCB inner layers to mid-frequency decoupling capacitors, low-frequency decoupling capacitors, and to the entire power supply. And it goes all the way up to the grid. So this is called as a depletion wave. And whenever there is a depletion wave and a demand, at that instance, that power has to be replenished. And it has to be replenished in time, in a proper time. As signal propagation is also measured in time, depletion wave also, it depends on time. It is time and distance. Yeah. Next page. PDN depletion wave causes and mitigation. That is the title given. Go to next page, please. Physics and mechanism of depletion wave. Key dynamic effects, especially on 112 Gbps PAM4 interface performance, and mitigation strategies in high density PCB design. Next page, please. When SerDes output stages an internal clock trees switch, they switch simultaneously. They demand the instantaneous power. The local charge consumption on the die capacitance. Now the decoupling capacitors will be within the package, actual package. So on the die capacitors will give the first instant power when it dips, they supply the power. And micro bump capacitance can be there on the redistribution layer. They give the next level. Now, when the power is consumed, the depletion wave initiates. Once localized charge is exhausted, a localized voltage drop occurs at the local via or a BGA pin. This BGA can be GPU or a CPU or whatever it is. Then radial expansion. This voltage drop propagates outwards towards the PCB power and ground plane layers through a cavity resonance in a 2D spherical or a radial electromagnetic wave. This is called as depletion wave. So at a very high speed PCB, we never talk of a current. We talk of a electromagnetic wave. This is what we covered in the last year. We were telling it's no longer electrons traveling. It is the EM waves. So that is why it is called as a depletion wave. Go to next page, please. Key dynamic effects, propagation velocity and breakdown of lumped models. The phase velocity Vp of the wave within the PCB dielectric is Vp is equal to C by root square of epsilon r. The C here is speed of light, which is a constant. So everybody knows what is speed of light, 3.10 meters for so and so. So that's where it comes. For a typical ultra low loss substrate material, epsilon r is 3 to 3.4. The propagation velocity is approximately 0.168 millimeter. It takes 1 picosecond to cover 0.168 millimeter, or it takes 6 picoseconds to travel 1 millimeter. Now, when we have a depletion wave, the decoupling capacitor should be within that distance. Otherwise, it takes more time. It won't reach in time. So we have to correlate time versus the distance, or we can call it as a gap also. The 112 Gbps challenge at 6 picoseconds per millimeter, a depletion wave takes 18 picoseconds to travel just 3 millimeter. A duration longer than the entire 112 Gbps PAM4 unit interval. The unit interval is 17.8 picoseconds. but it is taking almost double. You can say 2.1 or 2.2 times. It is a 3 millimeter. So 3 millimeter in a realistic terms, in say in mechanical design or even a PCB design, 3 millimeter looks like an acre actually. I mean, if you are given a space of 3 millimeter in a BGA or something, it is very huge actually in terms of high density packaging. So that's what it takes. It is about 2.2 times. So the next set of power decoupling capacitor, the replenishing capacitor should be available within that distance. Otherwise, it won't work. Okay. Since a decoupling capacitor is placed centimeters away, cannot respond with multiple unit intervals, the PDN acts purely on a distributed wave propagation medium rather than an instantaneous reservoir. The power is available and it be available at a distance and at a time. Otherwise, it is useless. Next page, please. 2D cavity dynamics and resonances. A behavior of a depletion wave in a power plane cavity is governed by a 2D wave equation for a thin planar waveguide. So I have given the equation. Let's give some time for people to look at it and understand what it means. In the meanwhile, I read the next 3 paragraphs. The wave front reflection, when the depletion wave reaches PCB board boundaries, plane cutouts are anti-pad arrays, the reflects back towards the driver with inverted array conductive phase depending on the boundary impedance. This is how even a signal trace goes. Signal trace sends a capacitive signature and an inverted inductive signature. So that's why the near end crosstalk is much more dangerous than a far end crosstalk. The same thing can be extrapolated for a power integrity. This is what I have mentioned. Standing wave and cavity modes. Multiple reflections, interface connectivity to create standing wave patterns, plane cavity resonances at a discrete frequencies. Basically, the gap between VCC plane and the ground plane has to be very less. And the gap between the dielectric gap between these two is called as a cavity. So this is how it works. Okay. Spatial crosstalk. If adjacent SerDes lanes reside within the same power plane. Now in some PCBs, the SerDes lines will share a ground plane with a power plane for a power decoupling ground, and a trace return path can be the same ground plane. They keep sharing the same ground plane. Or sometimes in some protocols, we use the power plane also as a return path. So this is the situation. If adjacent SerDes lanes reside on a same power plane as a reference, the expanding depletion wave from line A arrives at line B as an external supply fluctuation induced line-to-line supply crosstalk. And this comes as power-induced jitter. This looks as a power-induced jitter. There are 3 jitters. So one of them is a power-induced jitter that happens purely due to the dynamics of a power and ground planes. Okay, next page, please. I have mentioned power supply induced jitter, PSIJ. Supply sags caused by the depletion wave change the propagation delay through SerDes CMOS driver stages, transiting voltage noise into domain deterministic DJ. So deterministic DJ is now it is called as a power supply induced jitter. It is very difficult to control this. PAM4 I asymmetry, because of switching transitions between intermediate levels 0, 1 to 1, 0 versus 0, 0 to 0, 1. You are switching high or low. Demand different transient currents. The depletion wave creates a level-dependent PDN rail collapse. So the power supply planes are called as the power rails. The ground, it is also called as a ground bounce. Ground will not be 0. It will be something higher than 0. Closing the upper and lower PAM4 eyes unevenly. So now you don't get a wide open eye. The eye is closed. The next page, please. Practical design rules for power integrity budgeting. Budget element, ripple budget, less than or equal to 20 millivolts. Numerical target is 8 lanes of SerDes lines we are talking, operating at 1 volt. So 20 millivolts. Mitigation strategy derive target impedance to 1.25 milliohms. This is some strategy. PDN impedance less than or equal to 1.25 milliohms, 100 kilohertz to 2 gigahertz range. This 100 kilohertz to 2 gigahertz range has got a valley of death that I'm going to cover after another 5-6 slides. Hierarchical decoupling, low ESL caps has to be used. Local droop depletion wave, less than 15 millivolts at package pins. Tight capacitor placement, stitched wires for both power and ground. Anti-resonance peaks less than or equal to Z target impedance, plus or minus 20%. Some people calculate at 10% also. Mix capacitor values, distribute the capacitors, and that I'll show another picture which we derived from the previous session. Add dampening. VRM transient, less than 10% millivolts step response, multi-phase voltage regulator modules, low source impedance. So VRM, the power supply module, also can instantly start stepping up the supply. So when we select a power supply module, we have to go for a multi-phase VRMs. So maybe they're costlier, but they save the day. I think we can take a break at this.
Okay. Give me 1 second. Let me stop sharing it. Then take a break here. Ladies and gentlemen, let's have a quick look at this video and we'll come back right away. Good morning, good afternoon, and good evening, and welcome back to the Friday Talk Show with your host Rajiv Kulkarni. Talking about electronics manufacturing globally and how the various market segments do have a effect on the electronics manufacturing. And today's topic is a continuous sequel of physics-based HSIO interface routing, and the episode number is 5. So with that said, we have Mr. Ambaprasad, who is technology expert and been in the industry for the last 4 decades and plus. And let's welcome back Mr. Ambaprasad again, and let's continue our discussion as we left where today's last slide. Mr. Ambaprasad, please let's continue our discussion here, and let me just share the screen again. Here it is, and I think you can see the screen.
This
Please.
next slide. Next slide.
Yeah.
1-1-1. Triple Nelson. So in cricket, whenever triple Nelson comes, one umpire used to jump. He used to think it is very unlucky or something. So triple Nelson. 111 slides are there in this episode right now. It can make a very good reference book if we dare to publish it. Okay. Mitigation in high density PCBs. Trigger correlated switching of multiple 112 Gbps lines. Large transients current. Less than 2 amperes per lane. So this is the requirement. Propagation, voltage droop moves across planes at a speed set by the plane inductance and decoupling capacitor distribution. Resonance, anti-resonance between cap arrays and a plane inductance can amplify droop. Basically, we have to use very low profile capacitors. Mitigation, hierarchical decoupling, bulk at the entry, mid-range, what we call as a tantalum capacitors at the free areas in the PCB, which is very hard to get anyway. Higher frequency is on the package, and highest frequency or ultra high frequency is on the die capacitors. They'll be inside the package. This we don't have a control on that. The actual the chipset vendor has already accommodated this. Tighter plane spacing and stitched wires to reduce inductance. Now the ground and power supply wires have to be alternate. They have to be adjacent to each other. They also reduce quality resonance. Distributed capacitor values to spread the resonances, frequency response. This is a very almost a 30-year-old recommendation. Nowadays, you cannot take it blindly, but still it works, but now it has to be simulated. Voltage regulator module co-designed to handle fast transients. So these are some of the recommendations. There can be some other secret sources also. Next page, please. This is again 30-year-old formula. Low frequency less than 1 megahertz. The voltage regulator module itself will be able to pump more current. It will be able to do. VRM feedback loop, bandwidth response lag. These are the limitations or a bottleneck in the third column. Then mid frequency 1 to 100 megahertz. PCB discrete multi-layer ceramic capacitors 0 to 01 or 01005. 0 to 01. 40 to 01 can reside in space of 10402. That is the size we are talking about. 01005 means 16 of them we can place in place of 10402 capacitor size. These are the sort of a densification we are talking about. Mounting inductance, L mounting inductance plays a very important role, and board via loop parasitics drive capacitor past the frequency response. Then that is the value of death. What is value of death? I will tell you. I'll show the image. High frequency 100 to 1 gigahertz. This will be generally within the package. The capacitors will be within the package. It will be in the package. For example, if you look at a BGA, BGA itself is a package. I'll show one image actually for a 2D package, but packages are available up to 5.5D. So I'll show the image. Then again, silicon deep trench on the die. These are all the capacitors. They are within the package. Package area limits the total available capacitance volume, die capacitance and package capacitance. So these are the equation. Long time back, there was an application note which said there should be a tantalum capacitor should be distributed within the width of a coffee cup. If you put a coffee cup, coffee cup will be hardly 2 or 2.5 inches. It should be within that. They say you have to put a tantalum capacitors within that. But now the package itself is larger than this. So the old thumb rules will no longer apply. Okay, I hope I cover this in the next sessions or something, but let's take the challenge what you are facing. Next page, please. Yeah. Next page. This is produced by Getatech Calce University by Madhavan Swaminathan's group. They gave a package level PDN for a heterogeneous package. This is we are talking of a 2D package, not even 3D. It's a very low level packaging. 2D packaging. They are given some, again, you can see on the left side, there is a red color off-chip voltage regulator module. Then you see inductance and capacitance networks. Then you see a BGA, then the package, then a C4 bumps. C4 means your BGA balls. Then the through silicon via, and then there are micro bumps at a second level in a 2D. Then there is an actual silicon which has been shown like a mesh. This is the schematic diagram of a power distribution network. But if you go to 3D, 4D, 5.5D, the number of inductance and capacitance will increase. Okay, and that's how it is shown. And again, on the left side, I have shown some images of how the power supply is routed within a package, not silicon, within a package. Okay, let's go to next page, please. This is what we were telling about even 20, 25 or even 30 years back. People were, the mitigation strategy was you have multiple frequency capacitors. You have a tantalum capacitors DC to 1 megahertz. It is a repeat image actually. Last time I told I'll be using this. You see in that pink region. Then in the light green region, you see 1 megahertz to 100 megahertz frequency response. Then high frequency, this will be generally within the package, 100 megahertz to gigahertz range. And at a gigahertz range, even the VCC ground planes, which are parallel, which are very tightly spaced, they give the much of the capacitance required. We have shown this. If we don't meet this frequency, the capacitors will act like an inductor. They are no more capacitors, they are inductors. So that's why they distribute the capacitors value. I have shown a graph at the bottom side. On the top side, I have shown a typical PCB cross section, how it looks like. We are having a tantalum capacitors, we are having electrolytic tantalum capacitors, then vias. In vias also, we put VCC and ground via adjacent to each other, which are intermixed. They also give a very good cavity resonance. Medium frequency, reverse geometry capacitor, high frequency capacitors. Then it is on the package. Then we enter the silicon. On the day capacitors within the silicon, on which we don't have a control. This is decided by the OEM. Okay, next page, please. Yes, valley of death of power supply distribution network for 112 gigatrons for HSIO boards. Though we calculate and we simulate the capacitors, we do placement properly, for whatever the reason, if capacitors don't perform, they don't give the required energy at that distance and at that time, this is valley of death. The capacitors are placed, they're just placed, they're just consuming space, they're not doing any job. And again, we have to do simulation again, and maybe we have to do relay out, or we may have to change the value of the capacitor, or we may have to change the stack up. This is where the simulation meets the actual physical PCB. Most likely, this will be covered in the proto run. When people go for a production run, this might have been sorted out. Okay, so this is the valley of death. Valley of death is there available for routing also, but valley of death for routing is easy to control, but valley of death for decoupling is very difficult to control. It goes into component level, stack up and whatnot. Okay, let's go to next page, please. Mitigation in high density PCBs, some suggestions. In 112 Gbps PAM4 high speed input output design, the valley of death in power distribution network refers to the mid frequency range, typically between 1 megahertz to 100 to 200 megahertz. This is where people do simulations at gigahertz range, and they think doing at a megahertz range is not necessary, but it has to be done also for the PDN. In this region, board level decoupling capacitors become ineffective due to loop inductance, while package or die level capacitance lacks sufficient energy storage, causing the PDN impedance ZPDN to spike above target impedance. I gave an example in the about 10 minutes back that you consume water in a gym, but it has to be replenished by the local the water tank dispenser which is in the room and the tank which is in the floor. Now you have a lot of water available outside the premises, and you have a demand at the chip level, but the mid-level, whatever the floor level tank, water tank is not able to supply. Water is there, but it is not able to supply in time and in quantity. So that's the analogy I can give. So this is a very good analogy. Thanks to Madhavan Swaminathan, he gave this analogy. Same thing I'm repeating here. The PDN frequency spectrum and domain handoff. Meeting a sub-milliohm target impedance across the entire spectrum requires a continuous handoff between different decoupling domains. First of all, your on-the-day capacitance will take from the package capacitance from a mid-frequency capacitance from low-frequency capacitance, and low-frequency capacitance from the voltage regulator module, and that has to be constantly getting replenished. Okay, so what happens? The mid-frequency is the one. It has to not only give to high frequency, in the meanwhile, it has to collect from the low frequency also. So this it is like a typical drum, mridangam. You hit on the left side also, hit on the right side also. So it gets hit from both ends. So that is why this is called as valley of death. This is a very, very critical to simulate. The valley of death occurs right at the structural boundary between PCB and IC package domain. So very close to the package, the capacitance distribution is very, very important. And many times OEMs will do the review and they have their own recommendations. If we don't follow this, so they don't guarantee the performance of the package, PDN wise as well as high speed wise. Okay, next page, please.
Looks like it is done. Or this one?
No, you just hit, it comes.
Okay, this one?
Yeah, this is the one. So this is a typical, yeah, next page. Correct. That one image came. Hit next page.
Okay.
Just to drag it. Yeah. So this is the last page. And again, as usual, this is the curtain raiser for the next session, which we may hold till some time later. Power supply distribution scheme for 112 Gbps HSIO boards. Scaled PDN decoupling scheme for 112 Gbps HSIO. GPU, I taken GPU as an example. GPU scale in a co-package optics package from board entry to chip level. From board entry up to chip, how we have to go, I will explain. Maybe in, as usual, maybe 10 slides or whatever it takes. This is just a image, how it works. We can see one board entry level, two PCB, array of capacitors, three we are seeing capacitors within the package, and four we are seeing a distributed capacitance in a heterogeneous packaging. So again, the whole idea is the valley of death. At that region, we have to give and take. That handoff is very much important. So that's all I have today. Power integrity is a very key subject. For every 10 signal integrity engineers, you find only one power integrity engineer, in at least in Bangalore. Okay, that much is the demand. So many SI will fail because of power fail. Yeah.
Very interesting discussion, Mr. Ambaprasad. Thank you so very much for continued support for Global Electronics channel, and also continued support in sharing the wealth of knowledge that you carry since the last 40 plus years. Ladies and gentlemen, Global Electronics Friday Talk Show brings every week a new topic about the electronics and electronics manufacturing activities. So next week we will continue with the second episode of data center and its impact on electronics, and that is with me. And also, if anybody wants to join the panel, so they can join the panel discussion and express your opinion, your views about the data center and its impact on electronics manufacturing. With that said, we will We will have to sign off today's episode, and we will be right back next week at the same time with the topic of data center and and its impact on electronics. And thank you once again, Ms. Ambaprasad, and thank you all for watching the show. I know sometimes it is difficult to watch the show continuously because it's a weekday still here in the US, and it's a week, almost now weekend starting in Asia. And so wherever you are, please take care of your health, and please keep subscribing the channel and share the channel link with your friends and your colleagues in the electronics community. Thank you one, and thank you all. Appreciate your support.